Welcome to Robotics TV, and of course what we will do today is to use a quadratic formula. Those quadratic formulas that we normally do in class, and of course when we're finished we just get a grade on a paper, but we never ever actually try and use it to do much in the real world. Well, today, based on the answers from my quadratic equation, I can allow the computer to automate my circuit for me. And of course, you can see that my devices are on for 1 second, and then they will be off for another second. Alright, so that is the concept. So, starting from here, making math fun, it's all about the idea of edutainment. Alright, so of course I'm finding this very, very fun. And of course, the reason for that is because I can use my quadratic formula to do something in the real world, which is of paramount importance in terms of, making relevance of some of our formulas that we're using. Alright, so these are some of the variables that we're going to be using. So float ANS1, this is going to be one of the answers that the students will put in after they compute. Alright, the specific question in their book. Float ANS2. Alright, I've put in another input as well, and this is another answer that you will put in to the computer here, alright, in this IDE, Integrated Development Environment. So these are going to be students' input answer 1 and input answer 2. And then x_1, this is going to be one of the root, the possible root of my quadratic equation. x_2 is going to be another possible root of my quadratic equation, and this is going to be computed by the IDE itself, as I am going to show the algorithm down below. So these now are your inputs. So for example, for a quadratic equation, you normally have coefficients a, b, and c. Alright, so constant numbers a, b, and c in your quadratic equation, and of course a, b, and c are what we're going to be seeing in the quadratic formula. Alright, so that's the concept. All of these are variables, and of course I define all of my variables to be a floating point number. When we're doing quadratics, it's quite possible to get decimals from time to time, so I generalize by allowing everything to be a floating point number. Alright, so on the void setup, I am configuring all my pins to be output. So pin mode 3, output. That means I'm configuring pin 3 to be an output pin. Pin mode 4, output. I'm configuring pin 4 to be an output pin. Pin mode 8, output. I'm configuring pin 8 to be an output pin. So all of my pins are configured to be output pins. And so I have 1, 2, 3, 4, 5, 6. And I have 6 devices. Alright, so if I click on code here, I have 6 devices that are connected on my pins. So from pin 3 all the way up to pin 8. Alright, so that's the first thing. First, and we go back to the code. So that is on the void setup. On the void setup as well, you can see that I have a line of code called serial.begin, and of course inside here is 9600. This line of code switches on what is called a serial monitor, so that we can see the numbers that are computed by the computer. Very important. So we know the answer computed, so that when we do the actual working out in our book, we can of course match it up as well. So if I click on the serial monitor here, based on the values for a, b, and c, I'm getting -2 for one of my answers for x1, and -2 again for one of my answers for x2. Alright, and of course I just use a simple case just to test my quadratic equation as well. So on the void loop, which will occur over and over, I have my algorithm. So here x1 is equal to -b plus the square root of b squared, that is b times b minus 4ac, and that's all divided by 2a. And then the next root of my quadratic will be x2 is equal to -b minus the square root of b squared, and that's what b times b means, minus 4ac all over 2a. So this is the algorithm that the computer will use to calculate the quadratic formula. So based on the result of this calculation, I can allow my computer, or I can allow my device to automate my circuit for me. So under the if statement, if x1 is equal to answer 1 and x2 is equal to answer 2, so answer 1 is going to be what the student calculate, and that is placed in their books, and answer 2 is the next route that the student will calculate as well. So once the student's calculation matches the computer calculation, what's going to happen is that I'm going to write this line of code. Alright, so that's ideal. So I'm going to activate some motors and some LEDs. So digital write 3, high means I'm putting 5 volts on pin 3. Digital write 4, high means that I'm putting 5 volts on pin 4. Digital write 5, high means that I'm putting 5 volts on pin 5. Digital write 6, high, I'm putting 5 volts on pin 6. Digital write 7, high, I'm putting 5 volts on pin 7. So once I'm placing voltage on the pins, alright, voltages that are bigger than 0, that is, it means that I'm switching on the device. Alright, so that's the concept. This serial dot print line x1 and serial dot print line x2 is allowing me to see the numbers that the computer is computing. So when I do the calculation in my book, at least I can check it against the computer. So I can go all the way back at the top and enter my inputs, which is what I would have calculated, or the student would have calculated, -2 and -2. So when the students place -2 and -2 there, it matches. Alright, so it means that x1 is -2 that the computer computes, and answer 1 that the student computed as well is also -2, and x2 that the computer computed is -2, and the answer for the second root that the student calculated is also -2. So what that means is that since this is true, alright, x1 is equal answer 1 and x2 is equal answer 2, it means that this line of code will be executed. Alright, so that's the concept. So here, a simple mathematical formula again is just controlling my device. And of course, I can write any code under here. Alright, so I just chose to make my devices switch on and off in 1 second intervals. And that's the ideal. So that is the reason for this delay right here. So delay means that all of the code written up above is going to be executed for 1 second. When I have digital write 3, low, it means that I'm putting 0 volts on pin 3. Digital write 4, low, putting 0 volts on pin 4. Digital write 5, low, I'm putting 0 volts on pin 5, and so on. Alright, and of course, this block of code will run for a second as well. So my lights will be on for a second and then off for a second. Alright, and that is the ideal. Else, if the student computed the wrong answer, then what I'm going to do, just to show that the circuit is working, I'm just going to allow all the lights to just stay on without blinking. Alright, so for example, if I stop the simulation here and I go all the way back up, say for instance, the students calculated and the students say forgot to put on the negative value here, forgot to put on the negative value here. Alright, for some reason, say they compute and they forgot to do that, what will happen is we should execute the code in the else block. Alright, so in else block, what happens is that the devices were instructed to just stay on indefinitely without blinking. Alright, so that's the concept. Alright, so the devices will stay on indefinitely without blinking, and of course, I will just change this line of code. Alright, so this comment, I'll just change this so that it matches up my new ideal. Alright. Alright, so all my devices will be on, and so that is the concept. So here I use an if-else ideology. So if the student computed the right answer in their books, I will allow the lights to blink. If not, else, alright, the light stays on continuously. So once the light stays on continuously, I know that the student is wrong. Alright, and of course, we can print that in the serial monitor as well. Alright, so that's the concept. So let's just go ahead and say, if once we get the else, we know that the student is wrong. So let us just write something here. The student gave the wrong answer. Right, so the student gave the wrong answer, and then I'm going to write here alright, so that's for that. So the student entered the wrong answer, so it's supposed to be -2 and -2, and the student entered 2 and 2. So when I start, right, so you can see, alright, what is being printed out. The student gave the wrong answer, please try again. Alright, so that is the concept. Alright, so that is what will be printed out on my serial monitor. Alright, and of course, if I wanted to still show the values, the student gave the wrong answer, I could also print out the student, alright, the answer that the student gave as well. Alright, I think that is a good idea. So let's just stop this and say, let us just print out what is the answer that the student gave as well. Alright, so to do that, I just need 2 serial line blocks. So since there are 2 answers that the students would have calculated, I'm just going to have 2 serial print lines. Alright, so I am going to have here, I'll just put ANS1, and of course here again, I will just put ANS2. Alright, so those are the answers that the student would have given. And so we're just going to allow us to see that also on the serial monitor as well. So let's start simulation and let's see what we see. Alright, so yeah. So that is the answer that the student gave. 2 is the wrong answer. It is actually -2 that is the right answer. Alright, so that's the concept. So if we stop the simulation again, and so if I stop the simulation again, and I put -2 here, and I also place -2 here, what I will see now is that if I go back to the simulation, alright, so I will just see -2, and then of course my devices will be on. What I can also do is under the if block, since that is the correct answer will be given under the if block, I can also just write a comment, so this is the correct answer. Alright, so let's go ahead and do that as well. Alright, so I think I already copied that serial block there. So let me put it all the way down here. Alright, so a quick enter. The student gave the, alright, let's just change this and put correct. Answer, alright, student gave a correct answer, and let's just keep it simple. And then we can start our simulation again. Alright, so we can start our simulation again. So if you like neatness, we can just allow that to be in line. It bothers me when it's not lined up. Alright, so it doesn't bother me anymore. Alright, great. So if I start my simulation now, let's see what happens. Alright, and of course the student gave the right answer, and you can see the right answer is -2 all the time. Alright, so that's ideal. And of course, if I change the values of A, B, and C, I would of course, alright, I would of course get different values, and that will of course depicting that I have different quadratic equations as well. Alright, so this is actually using quadratics. So you're in class, and of course you have a quadratic equation. What you can do is to use a quadratic equation to make certain right? Calculations, and then so we can use quadratic equations to do circuit automation as well. So here again, mathematics, computer science, electronics, automation. Of course, once we have automation and we're using code to control hardware devices, we are typically doing robotics as well. Alright, so that's the concept. So just to guide through the code so that you can use it in class. And so it is for one of those days you are finished with quadratic equations. You go to Tinkercad, you already have the code, and then you will just allow the students to, of course, alright, compute, use the quadratic formula, make their computations, put in the values for A, B, and C, and of course input their answer, and then they should see the circuit being automated once their answer is correct. And even if their answer is incorrect, the computer will tell them, and of course they will still see that an incorrect computation will just still make a certain type of activation. For this example, that activation is that the circuit will be on, and of course when the circuit is on, it will just stay on. It will not be blinking. Alright, so for our little example, once the student is correct, the device is switched on and off in 1 second intervals, and once the student is incorrect, the device will just stay on. Alright, so that's the concept. So under the if statement, so this is the algorithm again. Alright, so to compute the root x1 and then the value for x2, and of course what we're doing here is we're checking to see if the value computed by the computer is the same as what the student will calculate, and we're checking again to see if the value computed by the computer is the same as what the student calculated. And of course this is how we choose to control our devices. We have 6 devices, and up here we are writing 5 voltage to each of these pins 3, 4, 5, 6, 7, and 8, right? And that's high. And then down here we're writing 0 volts to the pins. So 0 volts means that we're going to be turning off the device. Alright, so that's the concept. Alright, and so this is how we can use quadratics. So it's one of those days in class where you already did all of the calculations on the board and stuff like that, and of course you can say, okay, what else can I do in this topic? What else can I do? How can I apply it to the real world? How can I allow this theoretical abstract mathematics to actually do something of significance in the real world? And of course this can be used, for example, to access a security system, access a door, access a gate, switch on a robot, activate a circuit, etc. So we can spin this many different ways, and this is just one way that we chose to spin it. Alright, so that's the concept. Of course all the coding is there, and of course if we play around with the numbers, alright, so I just use A as 1, B as 4, and C as 4. If we play around with the numbers, we will see that we can get different quadratic answers as well. So for example, the quadratic formula that says x squared plus 2x plus 1 is equal to 0. If we solve that, right, we know that A is equal to 1. Alright, let's start the simulation a bit. A will be equal to 1, B will be equal to 2, and C will be equal to 1. And so I've just changed the values for A, B, and C. And if I start my simulation, let's see what will happen. So I start my simulation, and what is happening here is that my circuit is just on and on and on and on. That tells me that, alright, the value that was there before is wrong. Alright, so negative 2 is what we placed there, and that is what we see on the serial monitor here. That value is wrong. So what we need to do now is to do our calculations. So when we put this in the formula, alright, so when we put A equal 1, B equal 2, and C equal 1 in the formula, we would have x1 is equal to negative 1 and x2 will be equal to negative 1. Alright, so that you would compute in your books. And when you compute that in your books, you will put your new answers here. So if you place your new answers here, let's see what will happen. So I think I did that in my head. Okay, good. All right, so yeah. So you put your new answers there, and of course, you can say the student gave the correct answer. The answer computed by the computer is -1 in this case. All right, so that's the concept. So again, we can actually just make a link between theory and application, mind and hands. And of course, these kits as well. So let me just close off here. These kits, of course, the student could physically build it as well. The circuit just as it is with Arduino, download the code as well and see their mathematical reasoning being played out in circuit. So once they were able to compute the answer that the computer would have computed for our quadratic algorithm in this case, then they can activate the circuit. Alright, so that's the concept. So we could think of it, for example, like a password, right? A numerical password, where once the correct sequence of numbers are placed in the computer, then we can automate certain circuits. But in order to get that sequence of numbers, we have to go through a mathematical process. Alright, so that's the concept. So this is how software controls hardware. Another thing that we will want to get to in detail is the concept of increasing the value of the resistance. So if I increase the resistance value, I can actually control the speed of rotation. So for example, let me just put this on ohms, and then if I place that on ohms, stop the simulation, place it on ohms, I should know that there should be a change in speed in some of the motors. So let me, for argument's sake, place this all on ohms. Alright, again all on ohms. So this is 1 ohm of resistance, which is very low. So I should be seeing some changes in brightness, etc. And I'm going to vary. Alright, there you can see one of my LEDs are gone. Alright, because too much current is flowing. Alright, so the LEDs get very bright. Alright, and of course, too much current is flowing through the LED. The maximum current that should flow is 20 milliamps, and what they're saying here is more than 20 milliamps is flowing. I think what flashes on is 38.4 milliamps. So that's the concept. And so once I change the value of the resistance, more current flows in the circuit in accordance with the formula V equal I squared, V equal IR, Ohm's law. And of course, I can fix this. Alright, so let's make the resistance go up to 100. Alright, so that LED is now okay. Let's put this resistance to 100 as well. Now that resistor is now okay. And let's put this one to 100 as well. But that is now okay. So these resistances, I'll place them at 100 as well. Alright, and of course, based on the resistance value, I can see that I can modify the speed of the motor as well. Alright, so that's the ideal. Alright, so notice how fast my motors are spinning, and of course, what I'm going to do also, I'm going to modify the time that the circuit is on for. So I can go down here. Delay 1000 means that it is going to be on for 1 second. So let's make it be on for, say, 3 seconds. Alright, so let's stop the simulation. Let's make it be on for 3 seconds. So let's put 3. And let this be on for you. Change this to 3 as well. Right, so my circuit should be on and off in 3-second intervals. So to see the change in speed of the motors when I change the value of the resistors. And of course, you can see that my LED is very bright. What I can do is that if I increase the value of the resistance higher, notice that my LED is not shining as bright. So you can observe that, and that is the concept of Ohm's law. So when you study voltage, current, and resistance, if the resistance increases, the value of your current will decrease. When you decrease the current in the circuit, it means that, of course, your devices will not have that amount of energy. And so you will see, for example, it manifesting in terms of a lower intensity light, as you can see here as well. So once I increase the resistance, that happens. If I increase resistance to 10,000, you can see that this resistor is even much duller now. Alright? And so if we go back to code, the essence of it was quadratic formulas. Alright? And of course, we're using quadratics in robotics. Now, how cool is that? Alright, so thank you for watching. Here at MathTronics TV. Of course, we will try to upload a video every week to keep our circuit automations going. So from time to time also, we will have different persons on a podcast talking about the different ways that we can apply this type of concept, this type of technology in the classroom, also in the real world, and where we can go with all of this wonderful robotics, AI concepts, and circuit automation. So thank you for watching, and I'll see you in the next one.